Hi everyone, my name is Lydia and this is what I wish they had taught me about econometrics and introduction. In this video, we're going to talk about the CEF decomposition property. More specifically, we're gonna split them into signal and noise, or as someone of you might have heard before, separating basically the predictable from the random. This video is going to be an intuitive presentation of the CEF decomposition property, which we will write as y equal to the expected conditional expectation of y on x plus the error term. Keep in mind, this is what we will call the signal. So basically, this is what we can predict in the variation of y through whatever information we have on x. And ultimately, the error term in here is our noise. And this is also that random part, okay? Keep in mind that every study, and every outcome, be that income, test scores, they can be split into two pieces. So basically, this predictable part coming from the signal and the unpredictable part. Okay, and this rule that I just wrote right now, this is literally the CEF decomposition property. Now, there are certain assumptions for the way that it is built, because this is always true, and it's by how expectations actually work. Okay, so the error term in here, keep in mind, it's designed in such a way that on average, it's a 0 for every x. So E defined so that on average, it's 0 for every x, okay? So what we're saying in here is that the epsilon I, or the epsilon, is mean independent. And I'm going to put this in a box because it's so important. This is a property called mean independence. This is what makes the decomposition so powerful, basically. So epsilon is mean independent of x, okay? And the way we can write this mathematically is that the conditional expectation of y on x is equal to 0, okay? Now, the implication for this is that ultimately this epsilon is uncorrelated. Uncorrelated with any function of the x, okay? And we can very easily show the proof for that, even algebraically, especially now that we have also learned about the law of iterated expectations. So the conditional expectation on x is going to be equal to, so the first step that I'm going to do is re-express the epsilon based on the definition of the CF decomposition that I have in here, which means that I can rewrite that simply as y minus the conditional expectation of y on x. Next, I'm going to apply the laws of the expected or expectation operator. So I'm going to bring the y separately from the rest. So I have the expectation of y conditional on x minus, now keep in mind, when I take them sort of out of the brackets, so I'm going to have the y conditional on x in here, and then I'm going to have the expectation of the second bracket, which would have been like expectation of y on x, conditional on x, which ultimately is just the conditional expectation of y on x. We can see in here that they are exactly the same thing, so this is going to be 0, okay? And this concludes basically the proof for the first claim that I made, that the epsilon is mean independent on x. To show the proof for the second claim that I made, which was like a bit of a consequence of the mean independence one, we can call f of x any function of the x that we have. And here is where we can use the law of iterated expectations and rewrite that as follows. So we're going to have the expectation of f of x times epsilon, because this is basically how we write the fact that they might be correlated with each other. This is going to be equal to the expectation. So here, this is the point where I'm applying the law of iterated expectations of these f of x times here the conditional expectation of the error term on x, and I'm going to close the curly bracket. Now, by the mean independence here, we know that from the first bit, this is equal to 0, which means the entire expression in here ultimately will be 0. So the second one, it's a very straightforward proof. And again, it's based on the fact that we already proved and we already showed that by design, the mean independence will hold. Okay, so by knowing this decomposition property of the CEF, we have a clean way of talking about explained and unexplained variation, and that will not apply just to the regression, but basically in all econometrics. Because remember, we said the CEF is basically the world's best summary signal. Everything else that we have not included should be just the static. Okay? I hope this has helped you get like a more intuitive approach to the CEF in terms of like how we're going to use it to explain like the variation in y based on x, which is something that you will see repeated in how we do interpretations for certain elements when we run the regression. In the meantime, I'm gonna very quickly show you also a graphic presentation before we conclude this video. So this whole idea of the mean independence can be described through this graph. The red line that I have shown to you in here, let's assume is just like the best linear presentation of the CEF. So I didn't try to do the CEF like non-linear like we've done in previous videos. So just assume this is like the a linear CEF. As you can see, we have in here the expectation of y, x given x0, x1, and x2, 3 values that we have. And as you can see, the CEF is cutting right here in the middle, where is the mean basically of your y variable for these x0, x1, and x2 values. So again, it cuts there through the means. This is like where the averages fall, and this is exactly what we said the CEF did. So for every conditional expectation, so for every value of x, if we kept all of the y variables, we'd find the mean and then connect all of these dots. Okay, so in this case, again, we've just taken a very linear CF, but the same would have applied even if it weren't linear. I hope that helps, and I'll see you in the next video.